it's sad that I cannot show the slides simultaneously with writing on the blackboard. Otherwise, it would be, of course, much better if I write formulas.
Were you recording while doing the presentation?
Oh, this, I don't know. By the way, I think somebody asked me, I have slides of this. So what I can give my memory stick. Actually, if someone has laptop, then I can.
Oh, why not with the secretary?
Well, I can give it to secretary. I don't know if she will do this or not. If someone wants to, you have it. Okay. So today we will discuss U1 symmetries. U1 symmetry and its applications to particle physics. So, as before, we start with definition of introduction of transformation. So, how we define it. So, we have some field I, and we may have in our theory several fields. So, I is just numerated fields in our theory. Then U1 transformations correspond to appearance of such a phase factor. And for conjugate field, we have transformation with minus Qi alpha at dagger. So this is at classical level. Alpha is continuous parameter, so U1 is continuous transformation. It is characterized by continuous parameter of transformation.
You mean phi I and phi I is star here.
So here is
no phi I. You didn't put the index.
Oh, so I put here minus sign.
Yeah.
So what you want to do also?
Phi I.
Oh, phi I. Sure. Thank you. So and Q I is some number associated with a given field. So if you have several fields in your theory, then you have in general several different these Qi, 0, 1, 2/3, etc., which is actually characteristic of the field. When we go to quantum level, it will be clear. So the transformation is I, Q, I alpha, and this is unitary transformation, and this is one dimension. So this is why we call this U1. Different transformations, which are characterized by different values of alpha, commute. Right, so that the U alpha 1, U alpha 2 equals U alpha 2, U alpha 1. And so this type of the symmetry is called a abelian symmetry. Mostly I will discuss global symmetry, which means that alpha doesn't depend on coordinates. In the case when alpha depends on the coordinates, this is called local symmetry. And so in this case we are talking about gauge symmetries. Under U transformation, field acquires the phase, but this is the same field, so we have no transformation of I to J, different field, so only the phase appears. And therefore we can write a transformation or more precisely infinitesimal transformation as I alpha, then Q1, Qn, F1, Fn. Okay, so this is when alpha is much smaller than 1, so I just expand the exponent and take the first term, and I need to write here, so 1, right? So it's 1 plus this. So this matrix Q can be considered as a generator of transformation, right? And due to the abelian nature of these transformations, this matrix is diagonal. And therefore, quantities which are staying here can be used to classify our particles. So that parameters Q which appear in the transformations, and we will see this better at quantum level, can be used to classify our particles.
By 1 you mean n by n identity matrix?
Sorry?
You have written 1 plus iota I alpha.
So I just expand this exponent, the first term is 1.
No, I'm saying that by 1 you mean n by n.
Oh yeah, so it's a unit matrix. Right, so it's a unit matrix.
It's not necessary.
Hmm?
It's not necessary. One times a column vector is.
But you cannot add 1 to a matrix. That's why.
Yeah, you can.
No, it's not defined.
So, what you want now? That's okay.
For me, it's a column vector plus a column vector. It shows you all of that.
So this is column, right?
Yeah.
And
One
this is
times
1.
column is column.
Yeah.
Matrix times column is column.
Yes, right.
But we're adding 1 to a matrix.
It's a representation.
So that's one matrix, unit matrix, which is okay. Now let's go to quantum level. So at quantum level, we define transformation as U, which is now operator of transformation, the field, and U dagger. So U minus 1, but since these are unitary transformations, we have U minus 1 equals U dagger. Okay, and that should be F prime. So this is how at quantum level we introduce transformations. U then can be written as exponent to have kind of analogy to what we have at classical level, I. This is Q some operator and alpha. Now if Q is Hermitian, then the transformation is unitary. Now, to have a correspondence to classical level, classical transformation, we require that U F U dagger I equals exponent I Q, I, our numbers, alpha and Fi. Using this equality, we can find another very important equality. And let us consider infinitesimal transformation. Then, for this, we have u, which is 1 plus I q alpha Fi, 1 minus I q alpha. And on the right hand side we have 1 minus or plus I q alpha and the field I. Right, so this is called infinitesimal transformations. So alpha is much smaller than 1. Now we can open this, and what we will get, so let me write q Fi minus Fi q should be equal to q Fi I. So you can open this, and so 1 cancels with the first term. I neglect alpha square term, and then what is left is q times f and f times q. So this is what you see here with minus sign, and then I cancel alpha. So that's what follows from the law of transformation.
You can write the left hand side in the form of a commutator.
Yeah, so sure. I want to do the following next, and then you will see why I can write it. Then I will act by this expression on the vacuum state. So what I will get in this case, I will get the first term gives for me q Fi. Now the second term, I assume that vacuum is invariant under transformation Q. And therefore, acting by Q onto vacuum, I get 0. And therefore, this is the only term which comes from the left-hand side, and on the right-hand side, I have Qi Fi. Agree? So I multiply from the right-hand side or acting by this equality onto vacuum state. Then Q acting on vacuum gives me 0. Vacuum,
when you say vacuum is invariant, you mean that it is actually annihilated by.
Okay, so vacuum means invariant when I have Q. Sorry, that should be actually probably shown. So acting on vacuum by my transformation, I should get the same. Okay, so this is invariance. Probably I missed somewhere. So this is invariance of vacuum, right? Which means transformed state is the same as initial state. Now let me again make this infinitesimal transformation. Let me leave this. Probably I should hit this. So this is 1 plus I alpha q acting on vacuum, and this is vacuum. Alright, so this is for infinitesimal. Now, the first term cancels with this, and what I will get that since alpha is arbitrary parameter, I'm getting here Q acting on vacuum gives me 0. Agree? So which means that in the case of unitary transformations, vacuum annihilates when I have acting by this operator Q. It gives me 0. So this is expression of invariance. Right? You are not sure, tell me what expression. So if you open this, you will get 0 plus I alpha Q 0 equals vacuum state. Then this cancels, and now I have I alpha Q acting on vacuum, which is 0. So alpha is arbitrary parameter, it disappears, and so I get this expression. Vacuum vanishes under acting by this Q operator, which is staying in this power of exponent. If I introduce this type of the unitary transformations, then the operator which is staying in the exponent, it vanishes the vacuum. In the case of symmetry of the vacuum, or invariance of vacuum transformation. So this is invariance, which leads to this equality. So coming back to our derivation, what we have starting from this law of transformations, we get the following equality, which means that Fi can be considered as eigenstate of operator Q with eigenvalue Qi. So it's important that parameter which is staying in transformation law for a given field eventually at quantum level becomes a quantum number which characterizes a given field. Okay? Which means that we can identify this Q operator with some physical quantity. Okay? So it's an important statement that Q, as it follows from this, can be identified with certain physical quantity and then these Q small are values of this physical quantity for a given field phi I. So the way how we identify Q with some physical quantity depends on assignment of Q. So we have some fields, and then we assign to these fields different Q values. And that actually tells us what is the physical meaning of this operator Q. And I will show you examples. So just remember this, and you will see how it is realized. before doing this, let me consider the system of the field. Suppose you have the state composed of several fields. A system of fields. So I have the state produced by acting of several fields onto vacuum state. So by definition, we did this before, the state is transformed by just acting onto this state by the operator of transformation. So this is how the field is transformed. So what we are doing, as we did many times before, we insert between these fields unit, which is u dagger u. Here is u dagger u, and here also one which is u dagger u. And so what we will have here, u phi I, u dagger, u phi n, u dagger, u acting on vacuum state. And now we are saying that our vacuum state, suppose the vacuum state is invariant, and therefore this is again vacuum. If not, then things are more complicated. So we have the cases when the vacuum is not invariant, but if the vacuum is invariant, then we have this. This means actually that Q, which is staying here, annihilates vacuum. Okay? Now what we have here is given by exponent I, Qi, alpha. And here is exponent I, Qn, alpha. And therefore, the result of transformation is described by U, I, and then the sum over Q multiplied by alpha, and then I have my total status F1, Fn. So which means that the state composed of several fields is transformed according to Q total, which is the sum of Qi. So which means that Q is Qi, or Q are additive quantum numbers. So this means that the Q number of the system of the fields is the sum over Q numbers. In contrast to parity, C parity, or just parity. And the difference is because, remember, the transformation was not under exponent. It was just a multiplication of our fields. And therefore, it was a multiplicative quantum number. Here, because the transformation of this Q are staying under exponent, instead of multiplication, we have a summation of these quantities. As usual, and I'm not going to repeat this, if Hamiltonian is invariant under U transformations, which means that this equals H, or it commutes with U, then that leads to conservation. Of Q number, which means that Q total in initial state should be equal to Q total in final state and the processes. Okay? So now let us discuss applications and different U1 symmetries. Applications to particle physics. Oh, I should delete this. So in general, we have several fields in our theory, many. And so Lagrangian is, or Hamiltonian is the functional of the fields. In general, we can introduce U1 transformation for each of these fields independently. So in general, we can introduce n different U1s. Say A, U1, B, U1n. So our theory, may have many different U1 symmetries. And different U1 symmetries depend on how we assign the charges to different fields. So these Q parameters, which I have introduced before, Q, let us call them charges of the field Fi. So depending how I'm assigning the charges to the fields, I can have different symmetries. Of course, I may have kind of not independent symmetries, but if I assign the charges in such a way that I cannot say for charge of this QA have a linear combination of the charges of other U1, then these are independent U1 quantum numbers. So to define a given U1, I need to introduce assignment of the charges. So A, so for U, B, I will have another assignment of the charges, which is Q, B, I. And what I was just saying that if assignments of the charges are linearly independent, then they would correspond to different U1 symmetries. If they are linearly dependent, then just one of these U1 is reduced to others U1. No need to introduce it. So everything will be clear when I'm giving this example. So suppose I have particles in my theory, which is proton, neutron, and let me give in even quarks, U quark, D quark, neutrino, electron, W boson. And I'm assigning the following charges: 1, 0, 2/3, minus 1/3, 0, minus 1, and here's W plus, W minus. This is plus 1, and this is minus 1. What is the physical meaning of this assignment? So I'm saying that I want to assign these quantum numbers. So this is my QA for different fields I. And I'm saying that there is U1 symmetry, Lagrangian is invariant under U1 symmetry with this charge assignment. What it corresponds? What is the physical meaning of this assignment? Tell me.
Electric charges.
This is electric charge, right? So which means that this assignment corresponds to UQ, right? Electric charge. Now let me give another assignment, like 1, 1, 1/3, 1/3, 0, 0, 0, 0.
Very on the
So I want to introduce another U1 symmetry with this charge assignment. And again saying that all these fields are transformed under U1 transformation with this exponent with these Q values, Qi. Yeah, so that would correspond, I give interpretation, this as baryon number. So U baryon number. Now, so, and these two can live in my theory simultaneously, right? So you have the symmetry with this charge assignment, and this is charge, and charge is conserved, and I have this assignment for another assignment. This corresponds to baryon number, and it's also conserved, right, in standard model, unless I have these non-perturbative effects. Okay, so, and these two symmetries exist simultaneously. Let me do another assignment. 0, 0, 0, 0, 1, 1, 0, 0. What is this? So this is lepton number. And we see all the symmetries. I have another symmetry that's UL. And so the symmetry of my theory will be U1 Q times U1 baryon number times U1 lepton number. And in fact, I can introduce even some other assignment. So when I'm saying that these assignments are linearly independent, for instance, I cannot write this assignment as linear combination of this one and that one. This means that I cannot reduce one of these U1 symmetries to other symmetries, U1 symmetries. This you need to check if you want to introduce another U1. Okay? And again, in the theory, I can introduce many U1 symmetries doing different assignments. So the only I want to need to check if my Lagrangian is invariant or not with respect to these transformations. And if I'm introducing something new, or I just introduce some symmetry which is not independent on other symmetries. So let me say a few words about the status of different symmetries, U1 symmetries. Okay. Now, so I've introduced the symmetry transformations and check if a Lagrangian is invariant or not. Let me say a few words about this U1Q. Actually, I can consider also electric charge as a global symmetry. It's kind of, plus we have a more powerful local symmetry for this. And presently, it looks like this is very good symmetry, so it's probably exact symmetry. And we are testing this by studying or looking for possible decay of electron into gamma and neutrino. So this is the test of this symmetry. So for the time being, we haven't found any kind of evidences for such a process. And of course, stability of atoms has give a good test for this. So otherwise, if you would have such a decay, then atoms would just destroy it. And the best bound for this is that lifetime of electron is bigger than 2, 10 to the 22 years. Now, baryon number. So this baryon symmetry. This U1 corresponds to baryon number. So we are looking for proton decay, which is one of the best tests for this. And for time being, the best bounds have been obtained by Super Kamiakande. And they are searching for proton decay channels like positron pi 0. This channel is very good because you detect the product, both products. So you have Cherenkov ring which corresponds to positron, but then pi is decaying into two gammas, high energy gammas, which also are detected. They're producing electromagnetic shower. So you have 3 ring events. This is the signature. And so they measure invariant mass. So if they see some events, they measure invariant mass, and if the invariant mass equals the mass of the proton, that would be the proof that they see the proton decay, this channel. And this is very good channel because it allows to have low background for these events. It's difficult to reproduce such things by just accidental background events when you have simultaneously 3 rings. So that gives you, therefore, the strongest bound, and the lifetime in years is that lifetime is bigger than 2 10 to the 34 and to the 34 years for this mode of the decay. Now, other modes are like, for instance, proton can go to positron, gamma, or proton can go to muon, mu plus and pi 0. For this decay, the bound is slightly weaker. Tau is bigger than 8 10 to the 33 years. Now there are mode of the decays like pi decay into mu plus and k0. For this mode, the lifetime should be bigger than 7 10 to the 33 years. Now let me continue. There's important mode, and it is dominating mode if you have supersymmetry, because in the case of supersymmetry, it may happen that the main mode of the decay is of this type, and you have neutrino and K plus. I think it should be antineutrino. And the bound is again quite similar, 7 10 to the 33 years. So in these decays, the baryon number is violated by 1 unit, but also lepton number is violated by 1 unit. And what is interesting that in all these decays, B minus L, you can introduce this quantum number as kind of combination of B and L, is conserved. Let's take, for instance, this channel. In initial state, B minus L is 1, right? And in final state, B minus L is also 1, because baryon number is 0, however, lepton number is minus 1. Lepton number of the positron, and therefore B minus L is again 1. So in all these decays, B minus L is conserved. So this is very typical for many grand unified theories to have B minus L conservation. People also look for baryon number violation processes with delta B equals 2. An example of this process is neutron anti-neutron oscillations. Of course, neutron anti-neutron oscillations are if neutron inside the nuclei oscillates, then it immediately destroys your nuclei. But these oscillations inside the nuclei are suppressed because neutron and anti-neutron have different energies because of difference of interactions of anti-neutron. Therefore, kind of comparable in sensitivity is just the search for neutron anti-neutron oscillations in the beam. So you produce the beam of neutrons and then see if neutrons are transforming into anti-neutrons or not. I don't think that I have even some numbers for this. But it's of course much weaker lifetime for this than this lifetime of proton. Now let me discuss lepton number. So we have the following leptons: nu e electron, nu mu lepton numbers. And then nu tau and tau. And we have introduced Le, which equals 1, 1 for these two, but 0 for other leptons and neutrinos. We also introduced L mu, which is 0, 0 here, 1, 1, 0, 0 here, and tau number. So these are actually very good lepton numbers in all the interactions, but those, apart from those who are producing the masses of particles, masses of leptons. And so that has been tested that this, the good quantity, that this is good quantum numbers, by looking for decays which I have discussed, like mu to e gamma, or tau to e gamma, tau into mu gamma. And in all these processes you have breaking of lepton numbers, so this haven't been found, and they have strong bounds on the lifetime. The branching ratio, remember, for mu e gamma is around several 10 to the 13. 10 to minus, soon it will be even better. 10 to minus 13, of course. Now, eventually we have found, oh, by the way, this means that once we introduce these conserved lepton numbers, this means that we have in our theory u1e multiplied by u1 mu multiplied by u1 tau symmetry. I should add that antiparticles have opposite signs of these quantum numbers. So this is a very good symmetry of strong interactions, weak interactions, and usual electromagnetic interactions. But as you know that finally we have found that these lepton numbers are violated, and oscillations of neutrinos, which are transformations of, for instance, nu mu to nu e, explicitly testify for breaking of these lepton numbers. Apart from these individual lepton numbers, and I will discuss this next lecture, we also introduce total lepton number, which is the sum of individual lepton numbers. So alpha is e mu tau. So this is total lepton number. And it seems that this is really very good very good quantum number, because we haven't found any violation of this total lepton number. Right? So even in these processes, even if we discover this total lepton number is conserved, and it is conserved also in oscillations. Now let me discuss how we are testing conservation of this total lepton number, and what would be the process where we can see the violation of lepton number. And I should say this is as important as searches for violation of baryon number. Remember, they are even connected very often. So let me discuss search for violation of lepton number. We think that probably violation of this total lepton number is related to Majorana nature of neutrino. So if you prove that neutrinos are so-called Majorana particles, then this means that lepton number, total lepton number, is violated. So Majorana produced the theory, one of the first theory, fermion, of fermions with just two components, not four components as there are, but two components. So in Majorana theory, fermion coincides with antifermion. So in our case, neutrino coincides with antineutrino, and Majorana neutrino is the one which is the same as its antiparticle. So antiparticle and particle coincide. So these are what we call Majorana neutrino. Actually, this feature has been used, for instance, in the 30s to explain that neutrinos do not produce any effect in our detector, because for Majorana neutrino, magnetic moment is 0 for exactly. If you have just one neutrino, not two and with mixing. But if you just one neutrino, then magnetic moment is 0. And actually this was kind of important feature because neutron has quite big magnetic moment. Neutron is neutral particle, however it has big magnetic moment, as big comparable with what proton has. And if neutrino would have big magnetic moment, say like electron, then you would see the effects of neutrino even before 20 years before its discovery.
Has it been tested for neutrinos that they have no magnetic moment?
Well, so they just do not produce ionization, they do not produce effects of interaction in medium.
So?
Which means that it should be very small, at least.
But it has not been tested.
It is tested because, again, so people have tried to find some electromagnetic interactions produced by neutrinos. And that hasn't been found. And therefore, neutrinos should have very small electric charge or magnetic moment, because photon couples with magnetic moment, and then you will have a neutrino with magnetic moment, gamma, say with electrons. So you will have such a type of interactions. So magnetic moment of neutrino at least 11 orders of magnitude smaller than this Bohr magneton, which is what we assign to electron. So this is the present bound. We don't know yet if neutrino has some finite magnetic moment. It should once neutrinos have the masses. However, magnetic moment is extremely small. What I want to discuss first is so-called Majorana mass terms. Remember that fermionic mass term in Lagrangian looks like mass, neutrino, and neutrino. That's what we would write as a mass term in Lagrangian. We can introduce left and right components. We can decompose neutrino into left and right components. And nu left is 1 minus gamma 5 over 2 nu. And nu right is 1 plus gamma 5 over 2 nu. So if you sum up, then you will get just nu, right? Now what is important? Remember we discussed charge currents. And charge currents have V minus A structure. That is just kind of lateral comment. And we had interactions like electron, gamma mu, and 1 minus gamma 5. And a neutrino. So we have such a current, charge current, right? So appearance of this 1 minus gamma 5 means that only this component survives, and this due to projection properties of 1 minus gamma 5 is not operating here. So which means that only left-handed components are participating in charge current weak interactions. Okay? So due to V minus A nature, only left-handed components participate in weak charge current weak interactions. And also only left-handed components of electron, because if you, well, first of all, it's clear or not?
Yeah.
So if you just insert into this expression for the current this, then this component will cancel because of projection properties. Now, for Dirac neutrinos, left and right components can be considered as independent components. We have four fermion theory. What is important that this mass term can be interpreted as transition. Oh, so let me, using left and right components, write this as M, and then nu left, nu right. This is as far as mass term is concerned. Plus nu right, nu left. So, inserting again this decomposition of nu into left and right components, and this mass term I will get this one, and cross terms will cancel each other again because of projection properties. So 1 plus gamma phi, 1 minus gamma phi. Agree? Okay. So this means that we can treat mass term as transition between left and right components. For instance, if you take this one, you have right, then it will go to left, and this is mass. Or the second is left, go to mass, and this is go to, nu left, and this is go to nu right. By the way, right components do not participate in charge current weak interactions. Actually, they do not participate in the standard model in also neutral current interactions. However, they still can be in the mass terms. Mass term is always constructed as this transition between left and right. So this mass is actually connecting these two chiral components. Okay? And in fact, it is not excluded that our neutrinos are Dirac particles. They have left and right components, and left and right components form this mass term. But right components do not participate in interactions with intermediate bosons, so they do not enter charge currents and also neutral currents. But still they are present. So, mass term is constructed as transition between left and right components. These are independent components for Dirac neutrinos, but we can use another possibility to construct mass term. And what we can do, we can take as a right-handed component of neutrino, not this nu right independent, but we can take nu left and make charge conjugation. We will have exercise, I think you have exercise to check what are these properties, how this change under C conjugation. So, then we can construct the theory using only left-handed components of neutrinos. This is essentially what Majorana implies, Majorana theory. So now we can write our mass terms, or Lagrangian mass terms, in the following way. The mass over 2. And then here is nu left C, because I do this instead of, I'm just, so let me see, I'm taking this term, and then instead of nu right, I'm writing nu left conjugate, and then make Dirac conjugation, and this is nu L, and plus Hermitian conjugate. Okay? So, and Hermitian conjugate, I prefer to write in this one. So that would correspond to such a term. And Hermitian conjugate would correspond to this one. So there's 1/2 here. And this is 1/2 here to have correct normalization of mass in a question of motion. The point is that you have Lagrangian, then you write the equation of motion, then you differentiate over the field. But this one is the same as this one, and therefore you will have factor of 2 when you do differentiation. And so to get correct normalization of mass in the equation of motion, you need to put here 1/2. So that can be rewritten as m/2 nu L transponent C minus 1 nu L plus Hermitian conjugate. So what I'm doing, I'm using explicitly this Dirac conjugation. So I have double conjugation, right? So that will give for me this nu L without any conjugation. But then this C matrix appear, which is, let me remind, it's I gamma 2 gamma 0. Okay? So we have mass term, constructed mass term of this form, which has the following properties. The first, of course, it is not possible to introduce this for, say, electron or other charged particles, because you would have here electron, and that would violate electric charge, right? Because since this is the term in Lagrangian, it gives you transitions, right? And only for neutral particles you can introduce this Majorana mass term. Agree? Because Lagrangian should have 0 electric charge. So all the terms in Lagrangian should have 0 electric charge. Otherwise you would have the processes with violation of electric charge. So that it's only for neutral particles. And it turns out that neutrinos are the only neutral fermions, at least in the standard mode. Of course, if you introduce some other extensions of the standard mode, you may introduce more neutral fermions. But this is the only fermion. And people think that the smallness of neutrino mass, which you have observed, is actually somehow related to this exceptional property of neutrino, that they may have Majorana mass terms and not Dirac mass terms. So this is mass term for 2-component neutrinos. And those correspond to different polarization. Neutrino and antineutrino coincide, right? But you still may have 2 different polarizations. This is particle with spin 1/2. Now the operator which is staying here, which has nu transponent nature, this C is not important, it has lambda number 2, right? Because each of these have lambda number 1, and therefore this operator has lambda number 2. And therefore the presence of such a term in Lagrangian leads to the processes with violation of lepton number by 2 units. So the first term gives delta L plus 2, and this second one, Hermitian conjugate, delta L is minus 2. Which means that you are expecting existence of the processes, if neutrino is Majorana particle, which violate lepton number by 2 units. So unfortunately we have this big delay with this. But anyway, we'll continue tomorrow. Questions? So what we will do with slides, I don't know if you want or not. So if someone has a laptop here, one can just write it, copy if you need this.
I can, store it in my email and then I will send to everybody.
If you want, yeah. Well, there are many files. I want you to give.
How
just
many of them?
I don't know. It's 30 different files.
Oh, okay, it's okay.
So, which means that you need to know the names. I think it's. It should be 19A and 19B. So 19A is for the first set. I think.
19A and 19B.
Yeah, it should be, but the first is Diploma and this is PowerPoint. PowerPoint.
Okay.
So tomorrow last lecture.
I just got them.
No.